Okay, in today's little tutorial, we're going to be looking at the following learning objectives. We're going to be talking about subatomic particles. Obviously, they're the particles inside an atom. We're going to be looking at electric charge and what it actually is. We're also going to talk about the units in which we measured charge, and a man who found the unit and did a lot of early experiments. And then we're going to be talking about what does it actually mean to be a positive or negative charge. We're going to talk about insulators, and also we're going to be talking about conductors and how to charge different objects. And then finally we're going to round up by talking about the conservation of charge. So let's get into it. And so what we're looking at here is, in today's lesson, we're going to be focusing on electrostatic or electric charge. It's very different from electricity. Okay, electricity is the flow of charge, and most of the stuff, or most of the content we learn is about electricity. But for this particular unit, we're focusing on electrostatic. And so what happens is you have these things called positive and negative charges. Now, they're not really like positive and negative charges, not like floating around these things with pluses and minuses on them. The positive and the negative is a system that scientists have created to be able to model the forces that they have seen and witnessed and observed. So scientists started off observing all of these different phenomena, and they asked the question, why? And so what they saw, the witness is they saw repulsion forces. So here the balloon is repelling this metal Coke can. And then they also saw that opposite charges attracted. Okay, so they saw these attraction forces, and they needed to explain it. And so they came up with a system to explain it, and this is where we could call that electric charge. Now, we have to understand the atom, because the atomic structure really determines an element or a molecule's characteristics in the way they act, or what they can possibly do in certain circumstances. And so inside the atom, we all know that we have these protons, and we have neutrons, and we have electrons. Now, scientists have modeled so that they've called the electron the negative charge, and they've called the proton the positive charge. And of course, a neutron is a neutral charge. Now, this is really important because the electrons really are the ones buzzing around in these like electron orbits. And if they lose, they can be lost. Okay, now they can be lost through friction. Just by rubbing an electron, we can remove it. Now, what that leaves an extra proton without an electron pair and a positive charge. So this is called a sodium ion, is when the actual element loses an electron and becomes positively charged. Some elements can lose multiple electrons and have a 2+ charge or a 3+ charge. And this means that there's an extra electron floating around somewhere that can be floating around, but usually is attached to another molecule or another element, which leaves that molecule element with a negative charge. And so what we have here is how we can use these electrostatic forces to actually charge different objects. So here we have a neutral metal plate, and over here we have what we call a metal sphere with lots of negative electrons on there. And those negative electrons, will be wanting to repel each other. So there will be electrostatic forces in here. Because they are all the same charge, they want to get away from each other. So as soon as they're touched to that metal sphere, they have a chance to escape. Here they're locked. Here they have a chance to escape. Now, earthing, we're going to talk a little bit about earthing a little bit later, but electrons always want to get back to the ground. Sometimes it's called grounding of electrical circuits. Other times it's called earthing. But the earth itself was always attracting electrons and has lots of free electrons actually as well. And so what you're left with is you're left with less negative charge on the metal sphere, but you're also left with an negative charge on the metal disc. Now we can continue to do charging by different manners, okay? So in this particular case here, we have a neutral metal sphere. We bring a negative object close to the metal sphere, and what we see is that the positive charges, even though in this particular case here, the positive charges aren't moving. Like if we go back to the atomic structure, the protons, they don't move. The electrons are free to move, but the protons are pretty, like especially in a metal or a solid, the protons are rigid and fixed in place. So it's actually the electrons which are repelled to the other side of the sphere. Now, if you then touch that side of the sphere, okay, the electrons run down the outside. This is called charging by induction. The reason it's called induction is it's not actually touching. There's no conductivity of electrons. There's no flow of electrons between the two objects, and we call this induction. And so what you're left with is a positively charged metal sphere, and over here they see that the charges are then space out. The charge distribution, we call it the charge distribution, is usually even on a metal sphere, okay, or it should be even if they're and in this case here, once again, it's not like these positive charges have rushed to this side. There would have actually been some electrons, okay, that were over here on these elements that have come across, okay, and made this less positive, okay, and more of a neutral charge in that respect. So it's still the electrons that are moving, but we just represent it as a positive charges that have evenly distributed throughout the throughout the insulator. Another way to do it is when you have two different objects that are neutral in charge. You can bring once again a charged object near one of the sides. The electrons will escape to the other side, and then you simply separate the two objects again. And then the final step is, well, if this is positively charged, we say that they're even distribution, and these electrons here will be evenly distributed as well. So that's charging by induction. So let's talk about insulators, conductors, earthing, and also semiconductors. So an insulator, if something is an insulator, it allows for no flow of electrons, okay? It means that the electrons are pretty much locked in to their orbits, and they're not shared very well in between each atom, okay? So matter is made up of many atoms, so insulators don't share electrons, whereas conductors allow the flow of electrons. Down here is a picture of metallic bonding. So what we see with the metallic bonding, we have the positive nucleus that is rigid and stuck fast. But we have these things called delocalized electrons, or sometimes called a sea of electrons. Now, they're free to move between these different orbits, okay? So the electron orbit clouds, they're free to move, okay? And they have the different electrostatic forces in between them. But that is actually the case, this is given an electromotive force, or if something was a negative charge, was put here as a negative charge, all of these electrons then would begin to flow in that direction. They would be repelled by that electric charge. And that's where we start to get electricity, and we'll talk about electric potential energy and electromotive forces in the next tutorial. We do have other things called semiconductors. Now, semiconductors allow for the flow of electrons in one direction. It's got to do with their molecular makeup. So they're usually doped, and it's usually silicon. And when I mean by doped, it means that silicon is mixed with other elements, which usually leave silicon with a hole in terms of a missing electron, or with one extra electron. And by having one electron, they're able to jump between each of the holes. I would suggest that you look up how a semiconductor actually works. There's a lot of good YouTube videos on that, and also a lot of good theory online. So take 5 or 10 minutes to work out how a semiconductor works, even though you will not be assessed on it. What you really want to know is, okay, a semiconductor usually allows for a flow of electrons in one direction, and it's usually used in computer chips or other electrical circuits. So, where did all of this work and theory from electricity come from? It came from a man called Charles Augustin de Coulomb. And he did a lot of different experiments with this attraction and repulsion force. So over here, we see a charge 1. Over here, we see a charge 2, and they have a distance between it, which we call r. Okay, what he proved, okay, is that the force due to electrostatics is equal to a constant, Q1 times Q2, divided by the distance squared. Okay, and he used this with a bunch of different experiments, and obviously this is a constant, Coulomb's constant, and it was experimentally proven once we did the different relationships between all of the different variables, they could work out this value for K, or Coulomb's constant. So the unit for charge is called a Coulomb. Now a Coulomb is a massive unit of charge, and how it's actually defined, usually current is defined as the change in charge over the change in time. So you would think that a Coulomb is actually a fundamental unit, but it's not. Okay, scientists have used an ampere as the fundamental unit for current, and they define Coulomb as the Q here. Q usually stands for electric charge, okay, is equal to the current times by the time. Now the fundamental unit for current is the ampere, and the fundamental unit for time is seconds. So a Coulomb is equal to an ampere second if you have to derive the fundamental units, which is really a little bit backwards. Once we start studying electricity, electricity is actually the changing charge over the change in time. So you would think that a Coulomb would be a fundamental unit, but it's not. Now, because this unit is so large, and it's a massive unit to provide 1 amp for 1 second, what we usually deal with is the elementary charge. Now, as we've discussed, scientists called the proton the positive and the electron the negative, just so their mathematical models would work. And so an elementary charge is 1.6. We usually just use 1.6 times 10 to the negative 19 coulombs. And that means an electron has a negative 1.6 times 10 to the negative 19 Coulomb charge, and a proton has a 1.6 times 10 to the negative 19 positive charge. Now what we realize is this electrostatic repulsion is very visible inside the atom, okay? In order for the electron to be going around, it needs to be accelerated to the middle of its orbit, okay? So there has to be an electrostatic force there to keep the electron in orbit. And so this is where scientists, once they started to understand the atom more, came up with the word electricity, because really it was the flow of electrons, okay, that made this phenomena possible, okay, a lot of the phenomena that they're studying. Okay, so the elementary charge, good to remember, you will be able to look it up, but it's actually called little e, okay, so you'll see a little e here. Don't get it, don't mix it up with the mathematical E, okay? E is Euler's number in mathematics, but E in terms of physics and electrostatics is the elementary charge. Now, how do they work out how much charge an electron had? It's a great piece of science and a really cool experiment. I suggest that you pause the video now, go and research Millikan's oil drop experiment. Okay, spend 5 to 10 minutes understanding how Millikan worked out the actual charge of an electron. It's really good science and will give you a deeper understanding of where this elementary charge came from. Okay, you're back. Hopefully you enjoyed reading about one of the famous experiments that worked out the elementary charge. Okay, but let's have a look at how we can calculate charge on an object and do a little bit of mathematics now. So, what we see here is we have a formula. The formula is that total charge on an object is equal to the number of electrons times by the elementary charge. Now, in this particular case here, we want that to be a negative elementary charge. That was a mistake. But, so, objects can the only thing that gives an element or an object charge is either the increase in electrons or the decrease in electrons. So here, the balloon, okay, has been rubbed on something. and it's picked up extra electrons. Okay, the metal sphere, okay, has then acted according to the laws of attraction and repulsion. Okay, the negative electrons are then pushed to the other side. Okay, and that has then pushed this metal sphere to the left, okay, causing it to go out. Now, how do we work out the charge of this balloon? Well, we count up the number of electrons that it's picked up and multiply it by the elementary charge, because we know the charge on one electron. Now, obviously, electrons are in abundance in matter and in objects, and there's millions and trillions of them, even in the smallest length of wire or piece of metal. And so here's an example where they're looking at, okay, calculate the charge in coulombs carried by 6.0 billion electrons. Well, 1 billion is 10 to the 9, okay? So 6 billion is 6 times 10 to the negative 9. All we're working out is the total charge. So the total charge here is equal to the number, which is the 6.10 to the negative 10 to the 9 electrons, multiplied by 1.6 times negative 1.6 times 10 to the negative 19. So there you substitute in your values and you get this answer. And be careful, make sure you express it to two significant figures, as they have used 1.6 and 6.0. You would expect that the answer is in also two significant figures. So let's have a look now at doing one yourself. Calculate the charge in coulombs calculated by 4 million electrons. Pause the video, work it out, and come back to see if you've got it correct. Okay, great. So you've done a little bit of mathematics. Hopefully what you realize is that the total charge is equal to the number, which is 4 million. Now we know 4 million is equal to times 10 to the 6. Okay, we need to know our prefixes. And then we're going to multiply that by negative 1.6 times 10 to the negative 19. And so the answer there, once you put into your calculator or worked it out, is 6.4, negative 6.4, times 10 to the negative 13. And this is coulombs. And make sure you're expressing it in two significant figures. Now, the next question is pretty much the same thing. Using the same formula, C is equal to the number times by negative E. Excuse my handwriting, I have got a broken hand at the moment. We can rearrange that, so we can work out that if we know the charge, okay, we can work out the number of electrons on there, and vice versa. We can rearrange that formula to have it any particular way we want. Okay, so the next question, pause the video, try it yourself, see if you can rearrange the formula given to work out the following answer. So, welcome back. So what we're doing here is we want to work out the actual number of electrons, and rearranging what we see is we work out the total charge, okay, and we can call this Q instead. Q divided by the elementary charge will tell us the number of electrons. So the charge in this case is negative 4.8, and that little symbol, if you had to look it up, is microcoulombs. Okay, and we're going to divide that by negative 1.6 times 10 to the negative 19. And the answer that we get is 3 times 10 to the 13. And that's the number of electrons that has been passed onto that particular object, okay, to have that charge. So going further, we're having a look at this idea of conservation of charge. It's very similar to the conservation of energy. So charge cannot be created or destroyed. It can only be transferred, okay, or broken down into different compositions, okay. So in order for this to happen, let's have a look at a simple case here of a proton. Now, we haven't spoken about quarks yet, okay, but a proton is actually made up of two up quarks and a down quark. Now, in order for this to have one elementary charge, this up quark, and this down quark, if we add their respective charges together, an up quark has a 2/3 electron elementary charge, okay, positive. So if we have 2 of those, that becomes 4/3, and the down quark has a negative 1/3. So overall, the proton remains as 1 elementary charge positive, whereas a neutron has 2 down quarks and 1 up quark. And so the down quarks have negative 1/3 each, so a total of negative 2/3, and the up quark has 2/3. So a neutron has 0 charge. We also see the conservation of charge in particle collisions and annihilation. Annihilation happens when a particle and its antiparticle combine. Okay, so a positron here combines with an electron. Now, the charges are completely opposite here. So the gamma ray photon that is produced has no charge because we've had a positive one here and a negative one there. We have a neutral charge on the gamma photon. Likewise, a gamma photon with enough energy can split up into a electron and a positron, a particle and its antiparticle, as long as charge is conserved. So in all interactions of matter, charge must be conserved. So this brings us to the end of the little tutorial today. Make sure you jump onto the rest of the website and check out some of the cool videos displaying electric charges, and especially the Van de Graaff machine and the lightning, and read through the chapter in the book and answer the questions.